Flowability is a property always asked for. It is a subset of the science of rheology, which is the study of how materials flow and deform. Commonly measured properties include viscosity, thixotropy, extrusion rate, and slump, but there are many others. The first property we will discuss is viscosity. Viscosity is a measure of flow normally associated with liquids. The most common units are centistoke, centipoise, and millipascals, seconds, but the last two are most typically used. The viscosities of some common liquids are shown here. Water, for example, has a viscosity of 1 centipoise. You can see that the scale does not seem linear. Olive oil at 85 centipoise would not be considered to be 85 times less flowable than water. For practical purposes, we categorize materials as highly flowable, flowable, controlled flow, self-leveling, non-flow, and non-slump. Viscosity is commonly measured with a viscometer or rheometer. Viscometers measure the amount of force required to rotate a spindle in a liquid material. This force will depend on the surface area of the spindle and the viscosity of the material. Larger spindles are used for lower viscosity materials. Rheometers also measure rotational force, but use parallel plates instead of a spindle. This measurement allows for very accurate measurement of a material's viscosity and uses small sample volumes. Silicone products commonly used in electronics have a wide range of viscosities depending on the product type. Conformal coatings and gels are typically less than 1,000 centipoise. Most encapsulants are 1,000 to 50,000 centipoise, and adhesives range from 1,000 to over 1 million centipoise. The lower the viscosity, the faster and further a material will flow out when dispensed. Applications that need fast fill cycle times will want a lower viscosity, while others that need to constrain the flow may need higher viscosities. Formulations needing higher filler levels to obtain desired properties will also have higher viscosities than materials with little to no fillers. Viscosity is an important property that dispense equipment manufacturers use to optimize dispense systems for customers' production needs. A material's TDS will show a typical viscosity, but products have a specified range of viscosities as shown on their sales specifications. Competitive organic products may have lower viscosities than silicones since they are supplied as monomers that must polymerize as part of their cure or because they contain solvents. Silicones are supplied already polymerized and most are solventless. Organic products often lower in viscosity substantially when heated. Silicone viscosity only changes slightly with temperature. Now that we have covered viscosity, let's move on to a closely related property, thixotropy. Thixotropy is defined as the ratio of a material's viscosity at a high versus low shear rate. The term thixotropy is often used interchangeably with shear thinning, and many of Dow's higher viscosity products list a thixotropy ratio on their TDS. If a material has little to no thixotropy, the viscosity will be similar at various amounts of shear. Low viscosity materials typically have a low thixotropy. If a material has a high thixotropy, it will flow when shear or pressure is applied, but remain unflowable after recovery. This is how gaskets and seals are dispensed, but remain unflowable after the dispense process. Many sealants and adhesives are designed to dispense as a bead or line with limited flow. Extrusion rate is used to describe how a material will dispense from a needle or nozzle. It measures how many grams of material will dispense out of a given size needle and pressure within a stated time. The common units are grams per minute at 90 psi from a 1/8 inch orifice nozzle. Both extrusion rate and viscosity measure a material's flow. So which do we use for a given material? Let's take these three considerations. First, extrusion rate is more commonly used for products that will begin to cure when exposed to the air during viscosity measurements. So it is very commonly used for moisture cure products. Second, viscosity becomes less useful of a characteristic when you get into higher viscosities of greater than 300,000 centipoise. Higher viscosity materials often will use extrusion rate as the metric for flow. Third, extrusion rate is a very useful value when dispensing from a caulk tube, as it can directly relate to productivity dispense cycle, while viscosity is not as easy to correlate. In general, automated dispense equipment suppliers use viscosity, while manual dispensing of high viscosity products finds extrusion rates more useful. A sealant with an extrusion rate over 300 grams per minute dispenses quickly and may sag slightly. One with an extrusion rate of less than 100 grams per minute dispenses much slower and likely has no sag or slump. Slump is our final flow topic. This measures how far a material sags when dispensed or extruded onto a vertical surface. A non-slumpy material will show no downward movement. These can be dispensed onto vertical surfaces and retain their shape even with a considerably high aspect ratio. We have discussed how viscosity, thixotropy, extrusion rate, and slump help to characterize how a material flows. These are easy to test and highly valuable in defining how products dispense across a wide range of applications.